Good morning. Welcome to today's webinar. We're broadcasting today from Cincinnati, Inc. And we're getting ready to start right now with 5 laser cutting techniques demystified. Everyone should have their audio set. There's some information there. If you have any difficulties with that, please see the screen. We're going to have a Q&A session at the end. However, there will be opportunities for you to ask questions as we go. Down there on number 2, you'll see how to submit your questions through the webinar. Just a quick introduction. I'm Robert Farrell. Seth Westfall will be the application engineer driving SigmaNEST today, and Scott Grindstaff will be the presenter. Software you'll be seeing today is SigmaNEST. Profile cutting software, nesting software. We'll see version 10. Today we're going to profile that. SigmaNEST is used for remnant tracking, nesting, and quoting. Today's webinar, you're going to see laser cutting, but the software also runs on many other types of profile cutting and bending machines. Turret press, CNC, and so forth. If you have questions about SigmaNEST or want to see more about it, you can go to our website, SigmaNEST.com. We also have a series of webinars coming up with some variable topics related to fabrication. You can get that schedule right off our website as well. Let's do a quick poll question here before we get into the agenda. I'm going to turn things over to Scott Grindstaff here momentarily. I think we're going to launch a quick poll question just to get a look at where we are. Okay, while we're waiting for that, let's just go ahead and turn it over to Scott. He's going to take a look at the agenda here and walk you through what we're going to see today.
Thank you, Bob. Once again, my name is Scott Grindstaff. I'm going to be moderating the SigmaNEST side today. Seth Westfall, the application engineer, is going to be running through the PowerPoint and showing us some of the stuff, some of these processes and procedures in SigmaNEST. As far as the agenda, the topics that we're going to be covering is cutting for multi-part bending. So we're going to line several parts up and stick them all in the press brake at one time. We're going to talk about what stitch cutting is, when it's used, how it's used, and 2 different types of common line cutting. Then we're going to discuss fly cutting and slug destruct. So some of these things that we're going to be talking is really to give you ideas how in your facility you can make things more efficient, even though you may not be using these exact techniques. Then we're going to turn it over to Cincinnati, who is going to be doing some live cutting out on their machine. So let's go ahead and get started with cutting for multi-part bending. What we do is, the concept and the idea of this is to generate a row of parts with a bridge cut in between there. And then we're going to stick all of these parts in the press brake at one time. And that eliminates some time set up for secondary processes. So instead of having to bend 6 of these individually, we can do it at one time. So Seth's going to turn it over here to SolidWorks, and we're going to start in here with a 3D part. It's a flat part that's been bent. And what we're going to do in SigmaNEST is import that part directly into our system instead of having to save it out as a DXF and losing track. We're always working with the parent part, so we never do lose track of what is the latest version of the part that's coming in. We'll define in the part parameters dialog the salient features of the part, such as material, thickness, quantities, and whatnot. So we're going to go ahead and hit OK. So that's going to flip us over to the nest real quick. And we're going to take a look at how these things are lined up. So they're nested right next to each other. And when we put the tool path on it, you're going to see we're going to use this feature here called bridge. And we can define that gap in or the width of the bridge in between these parts that's going to allow us really to break them off. We're using a little bit wide gap right here just so we can see it better. You know, we'd use a much smaller gap in reality. So we put the tool path on it. We're going to simulate the cutting so you can get an idea of how this looks. So the first thing that we're doing, we have the option in SigmaNEST is to mark all the parts. These could define where the bend actually happens. Will help align things up with the backstop. So then we're going to come around the first part, and you're going to see we're going to jump over the top of all of these parts in order to accomplish this. So that's one technique, multi-part bending, that should help. We have a video here how that would look once it comes out of the laser onto a press brake, really summing up the whole idea. And we're going to wait for that to bend here. And we can do as many of these in a row as practical. It really depends on the part. The next item that we're going to talk about is stitch cutting. This is very interesting form of cutting. That if you're doing HVAC work and you have this gored elbow, SigmaNEST has a product called Develop that will actually, you can define this product and flatten it out onto a sheet, yielding the image that you see here on the right. And you can also see the lines kind of going through this part. You'll see it better here when we pull up the workspace. So what we do, and the idea of this is to cut these things and position these parts all back on top of each other, and it forms a square such that when we cut through the middle of one of these things, it is a form of common line cutting, but we also have a tab in there to hold the parts together. So now we can roll this entire set of parts up in one shot. Once again, thinking in terms of the next process to decrease time there. You want to go ahead and simulate that, Seth? I believe everybody gets the idea. We would finish up these other lines and go to one of the corners and cut around the outside, therefore freeing up the part, and then we would move it on to the roll former. Now we're going to take a look at a couple different types of common line cutting. Common line cutting is really used to decrease time on the laser. And there's many other reasons, pierce reduction, but in high volumes of parts, decreasing cut time on the laser can have a major impact on how many sheets you put across that machine in a day. The two types of common line cutting that we're going to look at is the cut rapid cut and one pierce two parts. Both of them are two different styles of common line cutting. One pierce two parts is a very popular type of common line cutting, but we're going to take a look at this cut rapid cut. So what we're doing on the parts on the left-hand side, you're going to see a row of parts stacked on top of each other. So the idea is to cut out that bottom part and then cut out the three sides of the parts on top of it. Now once that part is cut, that is completely free and separate from the rest of them, and this type of common line cutting actually not only decreases cut time, it actually increases part quality versus other styles of common line cutting because you are able to remove it. We do have options as well on cutting all the holes first and then come back and doing the common line cutting. So let's go ahead and take a look at the one pierce two parts. On these other parts that we see, in some cases it doesn't lend itself to doing other styles of common line cutting. Just putting one part back to each other is as good as we're going to get, such as the parts that we see here. You'll see that we're going to cut out both holes, cut straight through the center, and then go clockwise or counterclockwise around to the parts depending on where the head sits. Once again, decreasing cut time and throughput on the machine itself. The next topic is fly cutting. It's not one that's used all that much because of the part geometry in itself, but fly cutting allows you to speed up cutting on repetitive patterns like the part that you see here. So when we have a row of lines or geometries, even on a hexagon, we're going to notice that repetitive pattern within the product and then be able to just cut straight up and down. Now what we do though, which Seth is getting ready to show, without using this function, we're going to pierce in each hole and cut around the contour. So let's clear that off and put the fly cut on there. So on fly cutting, when we simulate this, we're just going to go straight up to one side and down the other and propagate our tool path up and down the y-axis while we go through there. You're also going to see that it's going to take into account those diagonals while they go through here. And it does look at the geometry related to the next part as well. And I think we're running kind of behind on the webinar. The whole point of this on CO2 lasers, we're just going to manipulate the shutter through this. On a fiber laser, we're able to just turn it on and off as we go through and cut the part out. The next item that we have is going to be a Slug Destruct. This is something that, this particular style of destruct is something that we just created with Cincinnati not too long ago for a particular prospect they were looking for. The point is we're going to come through this, go down through the lead-in, cut around the outside of this internal contour, having everything fall through the slats. What we've done though is we took this part, and this is obviously a smaller portion of a larger part. We took this part and stacked it on top of each other, and what we tried to do is kind of put everything together with what we've discussed here in this few minutes. And you can see that we have the Slug Destruct, where we're coming through and destructing that internal. We're also cutting this group of parts with a common line cut. I think we're falling behind here. While this is running a little bit slow, the tool path and how we cut these parts out, these internals are going to be important. It's important that we don't go, from horizontally down here to avoid that long rapid down at the bottom. So being able to move up and down these things and deal with them in columns rather than rows saves quite a bit of rapid time. Now once we have this last internal cut out, we're going to common line cut the rest of the parts as we zigzag our way down through the bottom. And then we'll part around the outside, but we have tabs on there that's going to hold the parts in place and keep the part from moving over onto another part or crashing the head. So that kind of concludes what we were going to discuss here on the software side. We're going to send it down to Matt out on the floor, and he's actually going to cut these parts live. So go ahead, Matt.
Thank you, Scott. Appreciate it. So everybody, I'm going to have a momentary lapse on your screen as I make some switches here, so just give me a moment. And I'm going to put on our webcams. That'll show you the different views of the laser here. I'm going to put on webcam number 1, which is going to be the mobile cam, and that I'll explain what that is. And I'm going to put on the other camera, which is going to be inside the laser. Okay, looks like we're good to go. You guys can see everything in there? Okay. All right, so appreciate Sigmatek offering us the opportunity to participate in their webinar today, 5 Laser Cutting Techniques Demystified. So what we thought would be a nice approach today is to show you what they actually showed you on the software, but do it on an actual laser. And in this case, we're going to do it on our fiber laser. So here's what we're planning to do on our side of it. We are going to just give you a brief introduction to our Seal 900 series fiber laser, which is on the camera right there, the mobile cam. And then we're actually going to do the same sequence that Scott did, but on the laser. We are going to do the cutting for multi-part bending. We're going to do the stitch cutting, and the 2 different types of common line cutting that Scott showed you, the cut rapid cut, 1 pierce 2 parts, fly cutting, and then also demonstrate the slug destruction. But then we're going to add another component to this, which is we're going to walk around the laser. We want to show you a little bit about the machine that we're doing the cutting on. And we're going to do a Q&A session at the end. So again, at any time during this presentation, type in your questions on the chat box, whatever they may be. We're going to allocate a little time at the end to answer some of those. What we're not able to get to, we'll be sure to follow up with you as well. And this event is being recorded. I had a few of you ask me that, and we'll make that available tomorrow. So I'm going to make some introductions. So let's get in front of the camera. I'm going to pull Todd Kirchhoff over here. And my name is Matt Garbarino. I'm the marketing manager here at Cincinnati Incorporated. And to my left is Todd Kirchhoff, and to my right is Drew Schneider, who's going to be running the laser for you. So always good to put a face at the name. That's kind of the neat thing we could do with our mobile cams. So let me get back behind the controls. And I just want to orient you a little bit with what you're seeing. We have 2 webcams active today. So one of them we call the mobile cam. That's got a set of wheels on it. We're going to rotate that around the machine after we're done doing the cutting. And then we have another camera mounted inside the enclosure that's called Seal 940 fiber laser. That's the one that's going to be at a 45-degree angle that you're going to watch the cutting from. There is a divider line that divides your camera or your webcam windows with your desktop, and you can make those larger or smaller. So take a look at that divider, slide it left or right or up or down depending on how you're oriented, and then you can adjust this as you need to. Now, before we get started, we have a couple poll questions. We always want to learn a little bit about you. And we are going to put a poll right up on your screen. And our question for you is, what is your current inventory of lasers? We saw from the earlier poll question that a lot of you are looking at lasers, may have them. We're just curious how many you have them, and if you do, are they CO2 lasers, are they fiber lasers, or perhaps you have both? So we'll leave that polling question up for just a moment. And I'm going to go ahead and close this, and then let's see what the results say. So about 18% of you do not have lasers. One thing I'd encourage that group to do, and we can follow up with you, we do a lot of Laser 101 type presentations to educate you about the different types of lasers. Looks like 60% of you have CO2 lasers. No surprise that that would be a large market. And then 7% of you have fiber lasers, and 15% indicated that you have both. So we appreciate you sharing that information with us. Also, we're broadcasting, so Sigmatek, although this is their webinar series and invited us, we felt logistically it made sense to do it from our facility here in Harrison, Ohio. That's where our headquarters is at. That's where we build all of our equipment. If you take a look at the mobile cam, we're looking at the Seal 900 laser, the 940, but I'm going to have Zach go ahead and pan to the left. This is our demo area. This is where we will bring customers to actually cut parts for training, and you'll actually see the meeting room's way back there. There's the Sigmatek folks back in that room. And then as we pan further left, you see one of our material handling systems that would go on any of our lasers. I have Zach pan back to the right. And you're going to see, again, one of our lasers, the 800 series. It's a CO2 laser. And then as you pan further towards the center, that's our 900 series, which we'll cut on. That's the fiber laser. We're going to continue right. There's our 400 series to the far right there. That's a CO2 laser. There's me, and there's Todd. And then behind me, actually we have a training class going on, but we have our ProForm press brake. We have our MaxForm press brake and BaseForm. So again, we invite you to come out here at any time, and this is where we'd actually show you our equipment and run any parts that you might want to have us do that. So I'll have Zach go ahead and orient it right back to the CL900. And the machine that we're going to be doing this demonstration on for you and cutting is actually the CL940. So the 40 designates that it's a 4,000 watt power source. All of our lasers since the mid-90s have linear drive motors with a rapid traverse speed of 12,000 inches per minute. They come in dual pallet configurations, 5x10, 6x12, and on some models 8x20. This particular one is a 5x10 dual pallet. The Windows touchscreen control is a very easy interface. In fact, we're going to show that to you on the screen in just a moment when I switch from this PowerPoint to Drew, and you'll see the actual control of the CL940. And Todd's going to give you some more details on this when he does his walk around. Again, this is a 4,000 watt power source, solid state fiber laser, fiber delivered, and it's a 5x10 cutting area. So what I'm going to do right now is I'm going to switch the desktop from my PowerPoint over to Drew, which is going to be the CL940. So you're going to have a momentary lapse on your screen. Drew, you're going to get a prompt.
Got it.
And go ahead and take it from here.
Okay, thank you, Matt. This is the control, HMI control. And before I do any cutting, I want to talk a little bit about our material library file. We are cutting mild steel, 036 or 20 gauge, and we're cutting with nitrogen. It's very easy for the operator to look at the material library file and get an idea of what parameters need to be changed. If I go to my Pierce tab, you can see that we're using no Pierce, so we're actually using Pierce on the fly, so we're turning the beam on and entering the geometry at the same time. If I go to my cut tab, here's our power, frequency, duty cycle. Our cutting feed rate is 2,015 inches per minute. Nozzle standoff is 25 thou. We are using a non-contact capacitance sensing head. We're cutting with nitrogen and 150 psi. If I go to my dynamic power control, a little bit about dynamic power control. We set up our DPC feed rate. It's currently set to 500 inches per minute. So essentially between 500 and 2,015 inches per minute, we're going to be cutting full power. And if you get into decelerating into a corner, or you have to cut features or holes less than material thickness, you have to slow down. And by doing so, dynamic power control acts as a dimmer switch to the IPG amplifier, and it will throttle the power up and down depending on the feed rate. So if we had a feature that had to cut less than 500 inches per minute, dynamic power control would sense that, it would read the feed rate off the code, and it would throttle the power down accordingly. If I go to my focus tab, this is an autofocus cutting head. We are using one lens. It's a 7.5 inch lens, and we're using an 80 thou high capacitance nozzle. We have the ability to adjust focus for our pierce, also for our cut. Because this is 20 gauge mild steel, we have all the settings the same. Let me just minimize this. So the first part we're going to cut is what Scott talked about. It's the multipart bending. And what you're seeing on my screen here is what we call our CNC Run Window. Everything that is green is a rapid traverse move. Everything that is blue is geometry that's going to be cut. And as it's being cut, it will change from the color blue to the color red. So an operator can quickly look at the screen and get an idea of where on the nest he is. Down here at the bottom, if you're doing multi-sheet nests, it'll tell you what sheet number you're on. And then right here, this is an estimation clock, so the operator would know how much time he has before this nest of parts is going to end to get a raw material sheet on the other pallet, or to get parts off the current pallet. So I'm going to go ahead and run this. I did actually, a lot of these programs, I purposely slowed the feed rate down so that you could get an idea of the programming techniques that Scott spoke about. We are cutting with the head down, so we're moving from feature to feature with the head down, and then the software notices that it has to wrap it back over top of itself, and it will automatically raise the head. So when this is done, it's going to jog the pallets out. You get an idea of our pallet exchange. We have two different pallets. We have a lower pallet and an upper pallet. I'm doing all the cutting on the upper pallet. So let me just quickly reach in here and pull this part out to give you an idea of. So that is the multi-part bending.
So just as we saw in the video a little while ago, you would stick these in against the backstops, which would be set appropriately, and bend all these parts at one time. Once they're bent, you'd be able to break them apart and continue on with your manufacturing process.
So I'm going to jog the pallets back in. The next part we're going to cut is the stitch cut that Scott spoke about. So on this one, it's cutting, doing curve cuts, and then it's essentially just leaving a little bit of a tab. And again, it's cutting with the head down.
As Drew removes this part, we're going to see that this is actually only a representation of what would be a larger gored elbow. We cut it smaller for conceptual purposes rather than cutting out the larger parts for an 8-inch diameter gored elbow. You can see right through there where we have common line cut these parts with the little tabs in between them. Again, we use thicker tabs just so we can represent it well on the video.
The third nest is the common line cutting. On the left here is what Scott referred to as the rapid cut, and on the right is the one pierce two parts. We threw this into one nest so that it would go ahead and cut, but it will give you an idea. It's going to cut everything on the left first, and it will cut the 6 parts on the right. Now these parts, I had Scott and Seth go ahead and tab them, so they may be a little bit more difficult to get out. But you can get an idea of just a small tab.
We'll also see in the common line cutting, as he removes those parts, there is no material left between the parts. So it is also a way to save an enormous amount of material based upon the volumes that you're cutting.
Okay, now we're going to get into some exciting stuff. The fly cutting part here, I'm actually going to run a couple of these. For So you can see on the screen, as it's cutting, the blue geometry is turning red, so you can get an idea of exactly how it's processing. So it's doing all the vertical lines first, and then it's going to come back and do the angled geometry for the triangle, and then it's going to do all the horizontal next. This works well on material where you can pierce on the fly, because you don't have that extra time where the beam is just sitting there, or the head is just sitting there piercing the material. Let me just run another one of these. One thing about our control is it's cutting up here in the top left. You can get an idea of the feed rate, the laser power, our focus position, our assist gas, and our standoff. So we're constantly giving feedback to the operator so he can diagnose any cutting issues that he may have as well. Grab both of these out. This gives you an idea of the part. So we've got rectangles, and we've also got triangles in here. Just gives you the ability to process parts a lot faster. So our final nest is the Slug Destruct, and this is the one where we worked with SigmaNEST to develop this technique. In a production environment, when you're doing slots and you don't have the ability to tab them, you do what's called a Slug Destruct. Well, typical programming softwares, they either want to do a Slug Destruct in the horizontal or the vertical direction. And by doing that, you are putting kerf cuts in there, and it adds processing time. So what this technique does is we have one pierce, and we're coming, I believe it's 4 or 5 thou from the edge, and then we're coming around and we're cutting the slot all in one motion. So it adds up the processing time at this, and also you have your Slug Destruct. And I believe we're doing 10 of them here. So it's going to go do all the slots first, then it's going to do all the horizontal cuts, and then it'll do the outline. So these parts are tabbed in here too. Let me see if I can just grab a couple of them out. So what's nice about this, they were all common line cut. So when you're done, there's very little material waste. So here we go. Here's all 10 of them, all lined up, and all the slugs fell out. Okay, Matt, that's it.
Excellent. So keep typing. I see a lot of you typing questions in. Keep those coming. Some are software related, some are laser related. So just keep adding those. We'll add some time at the end to handle those. What I'd like to do now is reintroduce to you our product manager, Todd Kirchhoff. And Todd is going to just talk a little bit about the laser you've been seeing cut. We're going to move the webcam over to the right side and put it right in between.
Okay, thanks, Matt.
And I'll let Todd take it from here.
Thank you. I just wanted to point out a couple of things here, and certainly the purpose of today's educational webinar is to make sure you understand some of the cutting techniques that are available and to describe what those terms mean. So thank you, Scott, for letting us participate in your webinar, and Drew for cutting those. Now, those parts that you saw programmed and cut certainly could have been cut on a CO2 laser, which is here on my left. We chose to cut them today on the fiber laser, but I just wanted to give you a quick overview of comparison of these two machines because certainly the software techniques could apply to either one. As many of you, it sounds like from our polling question, are already familiar with CO2 lasers and have those machines and how they, I wanted to give you a comparison how they compare with a fiber machine. So this machine here on my right, your left, is a machine that Drew just finished cutting on. And if you look at these two machines, they are the identical frame. They have identical drive systems and identical CNC PC operated HMI controls. So from that standpoint, you wouldn't be able to tell those apart with that commonality. However, the main thing visually that you'll notice is the different styles of enclosures on these two machines. On the CO2 machine here to my left has a plexiglass type of an enclosure, see-through enclosure, and that's because the wavelength of a CO2 is a longer infrared wavelength and requires a different type of guarding for your eyes, and that certainly works well to protect you from that longer infrared wavelength. The fiber machine on my right has a shorter infrared. It's still out of the visible spectrum. We can't see it with our eyes, but we do need to fully enclose that, and there is a small window on the front. Over here, you may not be able to see here on your screen. That is it shows up as green when you're here to see that. That is to block the far end of the visible spectrum and then into the infrared to make sure that it's eye safe. There's some more windows on the other side where Drew was standing when he programmed that. So that is one of the main visual differences. But as far as an operational difference, there are some differences here. And I'm going to see if Zach can come a little bit closer here and point out something. What is different is the power source of these two types of machines. And on this side, you see on this light gray box, this is the power source, the fiber laser amplifier, as we call that. And just over my shoulder here on the back end of the CO2 machine, you see a larger, darker gray box. That is the resonator, the CO2 resonator. So what's different on these two? Well, on the CO2 machine, we have gas bottles that would bring the laser gases into that resonator. There's a mixing panel to get the proper mixture of those gases. There's some high-speed fans or blowers or turbines, whatever terminologies you're comfortable with using, that will circulate those gases through those glass tubes at a very high speed, and then a very high voltage electrical voltage is applied to that and develops a current and generates then the photons that create the laser beam. So there's some maintenance costs and just some maintenance management associated with the CO2. On the fiber laser, it's a little simpler system here in that instead of having the glass tubes and the gas circulating through that, they're all solid state laser mediums here, and that is a glass fiber that's doped with an element called ytterbium, and that is, instead of high electrical voltage directly to a gas or to that medium, what we do there is we hit it with a very high intensity flash lamps, and that's what excites the ytterbium atoms in that glass and creates the laser beam. Now, getting the laser beam from the power source to the cutting head. That's another big difference between these two technologies. On a CO2 laser, we take that beam out of the laser resonator, send it through some tubes and bellows, off some reflecting mirrors, and direct it down to the cutting head and then ultimately onto the material. On the fiber laser, our beam delivery system is housed inside of this cable carrier. There's a fiber optic cable that's located inside of here. It's actually very small itself, the glass fiber itself. There's protective cladding and such that surrounds that. But as you see, this can be flexible. This is flexible now, and actually we are taking that out and through the floor and back up into the resonator. So here, instead of opening up the cabinet and seeing glass tubes, what you see here is a completely solid-state modules. There's multiple modules. The laser beams that are created in those individual modules are combined and then sent through the fiber optic beam delivery over to the cutting head. So that is another just a difference on these two. And again, this is a software cutting technique webinar. We do periodic technology webinars for you on the lasers if you want to learn more in depth of that. But certainly as you evaluate the two types of systems, both parts can be cut, certainly with different parameters and different cutting speeds, etc. And there's also a difference in the price point that we can consult with you to see which of those two systems might be most beneficial to your application. So that's a quick overview of our laser systems. And with that, I'll turn it back over to Matt.
Excellent. Thank you, Todd. And we got just a few more things before we wrap up with your questions. We wanted to ask you another polling question. I'm going to put this out on your screen right now. And that question is, what laser cutting techniques would you like to utilize? So based on what you saw today, maybe some of these techniques you're not using, what would it be most applicable to you? We'd like to learn about that, and we'll share those results here in just a moment. Okay, I'm going to close the poll, and I'm going to launch it to see the results. So over half of you were very interested in cutting for multi-part bending. I saw some good questions come across on that. We'll take a few of those. 23% for stitch cutting, 49% on cut rapid cut, 67% one pierce two parts, and 53% for fly cutting. So it's good to see that a lot of you are seeing advantages to go into some of these techniques. So I'm going to go ahead and hide these polls. And that essentially concludes our webinar today. What we'd like to do now, for those of you that want to stay and type in additional questions in your chat box, we're going to go through a few of the ones that you've already entered in. We'll take care of those right now. For those of you that would like to exit, you can do so. Again, this event was recorded. I should have that available tomorrow on Thursday for you. It'll be emailed to you, and it'll be available on the websites of both companies. So with that, I'm going to have Todd and Drew and Scott stand over here by the camera. And we're just going to go through a few of these questions here. And let me pull that screen up here in just a moment. Turn this camera off. There we go. And the questions that we don't get to today, again, we were able to capture these in a report, so we want to follow up with you and be sure we get you answers to everything. So I guess what we'll try to do is we may have to bounce around a little bit to try to group some of the software questions and then some of the laser questions. Let's see here. Let's start with a few of the software questions. So there was a couple questions on what are your thoughts or opinions on what parts are good or not good for common line cutting? Scott, maybe you might be able to talk a little bit about that.
Well, it depends on the application and the part in itself. Anytime you've got a large volume of parts and you're trying to fill up a sheet, obviously everybody's trying to minimize scrap. So anytime you have two flat portions of a part that could be mated next to each other, would be a perfect opportunity to common line cut.
And another question on the software is the common line cutting handled, should it be handled in the solid model or the flat CAD system, or should all that be handled in SigmaNEST?
That should definitely all be handled in SigmaNEST. What we like to receive is a true actual representation from the model into SigmaNEST. So we want an 8-inch part with a 1/4-inch hole to actually be represented by an 8-inch part and a 1/4-inch hole. And from there, we're going to go ahead and nest those parts. We're going to call that part a candidate for common line nesting. there may be some circles on that same nest with or other geometries which may not be common line cut. Those will be designated for regular nesting. So we do have variable part spacing while we nest for common line cutting.
Another software question for Scott would be, today we saw parts being cut on the Cincinnati lasers. Are there any lasers that are not good for common line cutting, or do you work with most manufacturers?
Most major manufacturers, we do work with common line cutting, yes. Across all the different processes as well, including plasma and water jet.
This is a software and a laser question in regards to part tipping. So there was a couple questions in here. I'll try to group these together and summarize them. Really has to do with how do you address part tipping, tabbing, and some of these parts. What's the best way to manage some of that?
Well, tabbing in itself, we can tab automatically on the lead-in. We can put a gap between the lead-in and lead-out, or we can manually place a tab on a part in a specific location. We do have automatic tabbing, which we can just count how many tabs we want on a part. Usually you're only going to have 1 or 2 tabs on there. On the particular nest that we saw, the last one with the Slug Destruct, we manually placed tabs right at the end of the parts to keep them from falling down within the slats and causing other problems.
And I think I would add to that too that obviously we don't want the tipping to interrupt the cutting process, but if we did have a very large part that did tip, we do have a means with our head with a magnetic coupling that would break away, and we can reattach to that and continue cutting without causing a lot of damage to the machine.
And another question regarding, again, common line cutting with regards to thickness. We did this on 20 gauge. Is it applicable for any thicknesses, or maybe speak to any comments on thickness of materials and common line cutting?
For the laser itself, you're going to have, you're only going to go so thick, 3/4 of an inch, depending on whether you're CO2, fiber. But as far as the software is concerned, it's the process that we're concerned about, not so much the thickness. Can the process, such as water jet, we can cut pretty thick with water jet, but it's going to be very slow. So it depends on that. It depends on the pressure and the garnet feed rate that you have going on that.
And I think that would be something that you would look at in application specific to see if there's anything on that part geometry that may not lend itself.
That is correct, yes.
So it's something to be evaluated.
I had a question on the CL940, just asking about capacities of the machine as far as thicknesses and types of material.
Yeah, when I mentioned some of the different technologies, or the comparison of the two technologies here, and there's a difference certainly in the enclosures and a difference in things. There is a difference also in the capacities and feed rates. On the capacity side, this fiber machine is rated at 1/2 inch for stainless, inch-mild steel, and aluminum. We can cut up a little heavier here on the CO2 with 1 inch on the mild steel.
A few questions on the Slug Destruction. Looks like there was a few questions asking about tabbing cutouts versus Slug Destruction. Is there one reason to do one over the other than the advantage of Slug Destruction would be a faster way to do it?
No, that would be the whole point in it, is the Slug Destruct of any type would be, of this particular type, would be faster than just a straight Slug Destruct that we have classically. This is a fairly new Slug Destruct, where we would cut vertical and horizontal lines within that internal contour and then pick back up and cut around the outside of it. So in that case, we're going to have a few more pierces, but having all of those internal contours fall through the slats rather than worry about tipping of that internal really can. All it takes is one tipped part and a crash head to save a lot of time.
Right, and on these thinner parts that you saw cut here, there is a dramatic difference in the feed rate. The standard feed rates on this fiber machine for 20 gauge were, I believe, Drew said 2,000 and some change there on the feed rate, and it's probably 4 or 5 times less than that on the CO2. So certainly, with the faster fiber machine, taking the extra time to cut the Slug Destruct is not as detrimental on the overall productivity as it would be maybe here on a CO2.
Had another question on fly cutting, asking what was the advantages again to the fly cutting?
It's eliminating pierces on each internal contour. We're also not stopping and cutting around each internal contour, the motion of the machine stays consistent as it goes up, and we don't have that pause right at the beginning. When we get to the contour, the beam turns on. Now we are cutting thin gauge metal, and that's really about the only time you're going to be able to use a fly cut is when it's thin, where the pierce time is almost negligible.
Another question on with regards to all the cutting techniques with common cutting is material utilization. The comment was that the speed is obviously, the process time can be reduced, but what's the benefit on material utilization? Is it substantial or negligible?
Oh, it's very substantial. If we put several thousandths, maybe 20 or a quarter inch even, in between parts, depending on the thickness of the material, being able to cut one line straight through there really can get you one or two more parts on the sheet, and sometimes that is a big deal. You know, it's free parts. And I know one of the questions, Matt, was to look at the sheet. I don't know if we can pan the camera over there. We'll do it here in just a minute.
Yep.
We'll look at where we common line cut those parts out, and the space is empty after getting 4 to 10 parts, depending on which one we look at.
And it also makes things easier when you go to remove the skeleton off of the machine.
Correct.
And dealing with your scrap skeletons.
Yeah, we had, as Scott said, we had a few people ask about just looking at the skeleton. So I'm going to have Zach bring the camera over to the sheet. Maybe Drew, grab a few of the parts you cut out and you could put next to the skeleton, just so you can kind of cross-reference where, you know, how that came out and what it looks like. I'll just have you back up just a little bit, Zach.
So there were 4
right there.
of the rectangle parts there.
So you can see that if these parts were cut out throughout the entire sheet, you know, even if we just did them in columns, that whole area that we see where there is no remnant, there is no skeleton, would be gone. Therefore, utilizing the most out of the material as possible. And even if we only talk about 3 to 5% yield increase throughout the year, that turns out to be a substantial number propagated throughout the year.
There you go. I'll have Zach just pan over to the left a little bit just so you can see all the different cutouts that we're done. We have a lot of other questions that are very application specific and would be best handled one-on-one. So like I said, we're going to capture this all in our report so that either Sigmatek or Cincinnati can follow up with you and handle these. So we're going to conclude today's event. We want to thank you for attending today. This, again, has been recorded. Will be made available to you by tomorrow.
I'd like to thank the Sigmatek team, Seth and Bob, and I'd like to thank Cincinnati for joining us, Matt, Drew, and Todd. We appreciate your participation in this.
Thank you very much. This concludes today's event.